Hello and welcome to the first video on electricity, where we're going to go in through the simple bits, the basics on what current, charge are and how circuits work in very simple terms. So the first thing we're just going to talk about or have a look at are the circuit symbols. So when we draw circuits to analyse how they work, to show how to set up circuits for practicals, we use symbols. Same reason as you might expect. In many cases, obviously, a lot of us scientists aren't very good at drawing, and so if we try to draw a battery or a lamp, you never know what you might get. So if we all use the exact same circuit symbols, we all know what we're talking about. Now, I'm not going to go through them individually. They're there for you to have a look at. You can obviously pause the video just to have a quick look at these. As we go through the rest of the electricity topic, we'll go through these individually in a little bit more detail. So, next thing, talking about this idea about charge. So charge, weirdly, has the symbol Q. So whenever we're talking about charge, and I'm being a lazy scientist as usual and I can't be bothered to write out the word charge, I'll use the symbol Q, which is obviously quite confusing. The reason it's Q is because when they were first looking at electricity, they considered it to be the quantity of electricity, so it's been given the symbol Q, not C, as you might expect. But what is charge? Well, it's a physical property. It's something that materials could have, particles can have. It can either be positive or negative. If it doesn't have either charge, then obviously it's going to be neutral. So you've got two types of charge, positive and negative. Neutral is no charge. And in terms of what we're looking at, lots of things can have an electrical charge, but the important thing for circuits are these electrons. So electrons, as in the same things that you'll have heard about when you're looking at chemistry and chemical reactions, ionic and covalent bonds and so on, they're the same things that are involved here. Now, when you place what we call a potential difference across a conductor, it can get these electrons to move. So potential difference of voltage is going to be important, but we'll explain that when we get onto current in a few seconds time, what I'm actually talking about there. So you don't need to worry too much about that at the moment. The units for charge are coulombs, and coulombs has the symbol of C. So moving on to current, right off the bat, I'm going to make things even a bit more difficult, because charge, coulombs, current all begin with C. They've all got different letters for their symbols. Current is I, and I is down, again, when they were first looking at electricity, they considered it to be the intensity of the electricity, so it's been given an I there. So what is current? In very, very simple terms, it's the movement of these electrons, the movement of these charge carriers. So we sometimes consider electrons to be charge carriers, but it's basically the movement of those electrons. Now, how does that happen? So we're looking at conductors here. So a conductor is going to be a material that allows a current to flow quite easily. So there's lots of different conductors, but in terms for electricity and circuits and GCSEs, metals are going to be the ones we're mainly looking at. So why does that work? It's because metals have these things called free electrons, which you might have heard before. So what we've got is a diagram of a metal. So we've got the particles or the ions here. You might be thinking, well, hang on, solids are always touching, the particles are touching. Well, yes and no. I mean, they're not really touching. We draw them as touching. I'm not drawing them, I don't have them drawn as touching here because it makes it easier to see what's going off. But what we've got are the solid particles, the ions, in rows, and we have these little guys. These are my electrons, and this electron here is free to move. Now what that means is it might be orbiting this ion for 1 second and then decide it wants to change and move to this ion and orbit that one, and then it might want to change and move to this one and orbit there, and so on. Now, just a little disclaimer, they don't really decide on anything. They're not conscious. They just move from particle to particle. They're free to move. Now, if I place a potential difference on this, what I was talking about before, if I get a battery here, I'll make one side of this positive, probably going to be very big, and I'll make one side negative. So if you've ever used a battery before, you'll notice that one side is positive, one side's negative, and circuits will only work if you have the batteries in the right direction. So this is why. So the positive is here, the negative there. The electrons have a negative charge, so that means they are forced away from the negative end towards this positive end. So the electrons will move from right to left on your screen, and that is the current. So in terms of a GCSE definition, current is the rate of flow of charge. In simple terms, you just need to know it's the movement of electrons, but you need to be aware that they could throw that into a multiple choice question, for example. You need to be aware that it's the rate of flow of charge. And the units are amps or amperes, and that's got the symbol A. Now, just a little bit about the formula. I do like to try and think of tricks that will help you remember the formulas. You're going to have to remember this one. And the way I always used to remember is if you are working out the rate of something, then you divide that something by time. So acceleration, for example, is the rate of change in speed. So you take the change of speed and divide it by time. Same thing here. It's the rate of flow of charge. So the something is the flow of charge. So you're going to take the flow of charge and divide it by time. So that gives me the formula: current equals charge divided by time. Now that is how I remembered it. The formula, generally speaking, gets written like this though, which is just the same formula as that, the one I would remember. It's written like this though. Now there's the triangle that would help you rearrange it. And just for later on more so, when you're using an ammeter to measure the current, it's placed in series. More on that later on. Which leads us to the last part of the video, which is about circuits. So I always use this simulation, which you might have seen before. You might have seen me use it in these lessons. It's by the University of Colorado. So if you ever wanted to use this thing, you go to University of Colorado, DC Circuits, and you'll find the link there. It's pretty good. It shows you most of the things you need to know. So this is not really a circuit diagram. You can click on circuit diagram and it gives you that. So you've got the cell there. This is an old school diagram for a lamp. We don't use those anymore, but I'm going to use the pictures so you can see what's going on. So we've got our batteries here. I've got two lamps placed in series, and then we've got the conductors, the wires going there, and you can see my little minuses, they're the electrons. So if we complete this circuit, you can see how a circuit works. So the battery is supplying a potential difference or a voltage, and what that is doing is it's causing the electrons to move, and as the electrons move through the circuit, they supply energy to the lamps and therefore they light up. If I was to increase, maybe if I can, there we go. If I was to increase the potential difference or the voltage, you can see the electrons have more energy now, and so they speed up, they flow faster, the current's increased. Loads of ways of thinking about this. There's plenty of models of how to think about electricity. None of them, to be honest, are perfect, but you quite often see this as a central heating system. So a central heating system can be used to model an electric circuit. Instead of a battery, you have the boiler. The boiler supplies the water, which are my electrons, supplies the water with energy, with heat energy, and the water moves through the pipes, transferring that heat energy to the radiators. Once they've supplied energy to the radiators, the water then moves back where it gets energy from the battery. Now, as I say, it's not a perfect model, but it does help you see and visualize how electric circuits actually work.